Assalamu alaikum. In the previous video we have covered how to basically apply the triangular load, and in this video we are going to cover like what is the effect of self weight. Okay, and we know that if the length of beam is too large, then normally we neglect the weight of the beam while analysis, but if the length is too large, then we need to consider this effect as well, as beam may deflect a little bit due to its own weight. Okay, so we can perform the same analysis using this curve here, but and for that what you need to do, you just need to go to the solid geometry here, and then you see there this is the mass. Okay, so you need to multiply this mass with the value of g, that would be equal to the weight, and then you can apply the distributed load here, and then you can compare, you would see how much deflection is there, how much reaction force is there, and you can compare that with by adding the weight effect. So let me explain how we can do that. Okay, I would just close it for now, and then let me just save the model, and then I will start a new analysis. Okay, for simplicity, okay, I will use a cantilever beam, okay, to study the effect of self weight, okay, because the cantilever beam experience the maximum deflection at one end. Okay, so I will keep the dimension like 200 by 300, and then the volume, this would become the volume equal to this one. The default structure state density in the ANSYS is 7850, so I would keep that. The standard gravity value is 9.0807, okay, meter per second square. So using this value, okay, so if you like I have the density, I have the volume, so by multiplying these two values we can get the mass. So by multiplying the volume with the density, you can get the mass, and then multiplying that mass with the gravity, you can get the weight of the beam. So this is the weight of the beam. Okay, so let's see how we can do that. Okay, so I would go to the ANSYS, okay, just from the system component, okay, system component, just select the geometry here, just drop it here. So I will use this geometry twice, so that's why I will use it, cantilever beam. Okay, so just open it. Okay, so I have the ANSYS mechanical, and I just change the units to millimeters, and then here I have how much. So sorry, let me close that, I don't need it now. So 200 by 300, and then 2000 mm. So XY plane, right click, look at, go to the sketching, select the rectangle. Okay, so this is rectangle, okay, that's fine, and dimensions, general, let me keep that to 200, and this one I will keep 300. So 200 mm, and then we have 300 mm, that's fine. Okay, so I have defined this geometry. Okay, so I would consider that as I need to extrude it, because I want to keep it as a 3D body, and then I want to consider the effect of the weight, so I will not draw it as a line body here. So for that I would just extrude command, and then this is my sketch, so I would select this sketch and then apply, and in the depth, okay, I will select 2000 mm. So then click on generate. So this is my cantilever beam here, and then okay, so I've done here. Okay, everything is fine. Okay, there's a line body, and this is a solid body. Okay, that's fine, just close the design bottler. Next is go to the again select the go back, select structure and drop it on the geometry. ANSYS would automatically connect these two. Okay, just wait a bit, what happened here? Okay, just drop it here. Okay, so ANSYS will automatically connect it. Now I have my engineering data, I have the geometry. Okay, just click on the engineering data. You see that this is the density 7850 kilogram per meter cube, so I kept the same. Okay, so if you change this value, if this value change, then you need to adjust. If there is some other material, you need to adjust the value here, or you can you see that add a new material. So just open the ANSYS mechanical. Okay, this is ANSYS mechanical. I need to draw the cantilever beam. Okay, for that I would fix this end, or okay, I would fix the back end. Okay, this would be fine. Okay, just click the static structure, click here, click on this face, right click, insert, and let me fix this board. Okay, so to add the effect of the gravity, I need to determine the deflection here. So just right click, static structure analysis, insert, and then here you need to add the standard earth gravity. Okay, so if you add this tool here, this boundary condition here, it means it will consider the effect of the weight. Okay, just look at here, right now the gravity is defined in z direction, which you do not want to. Okay, you need to change that. You need to define it in the negative y direction. Okay, so just click the direction here and then change it to minus y direction. You see that now the gravity is downward direction. Okay, this is what I have done. So just I will create the default mesh here. Okay, because that's not a big deal. Okay, and then I would solve my model here. Okay, so the mathematical model is solved. Okay, it's just I would to consider that I would just I want to determine the directional deformation, and I would also add basically how much reaction force is there at this port. Okay, the fixed port here, and to add that I would also add the moment reaction. What is the moment reaction due to the weight? And then I would also add the stresses as well. Okay, the stresses introduced due to the weight of the beam. Okay, so right click and evaluate all results. So you see that, okay, this is the directional deformation. You see that this is in units. Okay, so just let me change that to millimeters. Okay, so you see that the maximum deflection here at the free end, sorry, at this end. Okay, because that end was fixed and that was free, so this is 0.1036. okay, this is due to the weight of the beam. And then you see that due to the equivalent stress, okay, this is the stresses are 3 megapascal, 0.03, and the force reaction, okay, which is basically the main indication of that the weight is acting on the beam. Okay, this is one. Okay, you see that the force reaction at this fixed end is basically 9238. okay, which is exactly was 9238 was the weight of the beam. Okay, and this, okay, so it means, okay, the weight is basically applying the force, and then this port is basically resisting that, so that's why the force reaction is exactly due to the weight. Okay, because there is no other force. Okay, so this reaction is due to the weight of the beam, and same, the weight is also producing the moment here, and in this case you see that the moment is about x-axis. Okay, because that's perpendicular to this surface, so this 9 to 9.236. okay, so that's the way. In this way you can consider the beam. Okay, for further strengthening, okay, though the force reaction says that my analysis is correct because that's equally to the weight of the beam, but I want to do the same analysis. Okay, just remove this standard gravity here. Okay, and then okay, so I can also do that. Okay, just remove this one and apply uniformly distributed load here of 9238, which is basically the weight. So I would, for the reference, I would just take the screenshot of these deformation here for your reference to compare my results. So what I would do to show you that, though I can start another analysis as well in the same, but I would just prefer this one. Okay, you see that, so this is my, you see that directional deformation. Okay, just copy paste there, and then okay, this is what I'm doing to compare the results only and nothing else. And then these are the stresses due to the weight. Okay, and then last one, force reaction is that's equal to the weight. So I will not take the screenshot here, but to show you, I would take the moment reaction. Okay, so because I would change this one only. Okay, sorry, I made the mistake. Okay, I would change this one only. Okay, so sorry. which is moment reaction. Select this one, this, and this. Okay, Control C and then Control V. Okay, so I have my results, and now what I need to do, okay, I would just delete this standard gravity option here, and I would delete this theta here as well, and now I would apply force of which is basically the weight of the beam. Okay, distributed load 900 and 238. So just right click, insert force, and then select this face, apply, and then by component, okay, I would change that to component, and then in the negative y direction there was 900 and 238. Okay, so 9238. Okay, that's quite right. And then now I would solve my model. Okay, just wait. Okay, so I have my model here. You see that first this is the force here. You see that the force action is exactly what was in the case of the cell weight. Okay, 9238, as you can see that this was equivalent, this is equal to my applied weight, and the moment reaction, this is 9238 10 raised to power 6, and here the moment reaction was 9238 10 raised to power 10 raised to power 6. So that's exactly here. And for the equivalent stresses, you see that it varies, the stresses varies from 0.001 to 3 megapascal. 3 megapascal. And here you see that the directional deformation varies the stresses. Okay, in the case of the it's 0.001 to similar, the maximum stress is 3 megapascal. So these are in range. You see that. And next is how much the direction deformation is 0.1. Okay, at the free end 0.1, and here it's also 0.10366. Okay, so that's almost correct. So this is how you can say that the weight acts on the beam, and it is almost a distributed load on the beam. So you can either add the weight effect by adding the distributed load over the beam, or you can just add the right click here, and then you can add this standard earth gravity option here. Okay, I hope you got that. You can also perform the same analysis with the I-beam section we have covered before. Thank you. If you have any question regarding this tutorial, you can ask in the class or just write in the comment. Thank you.